Today we are going to talk about operators in quantum mechanics. An operator is a symbol, like this square here, that tells us to do something to the function on its right. This symbol can be anything: a letter, a group of letters, or any typographical character. You may feel like operators are new to you, but if you have taken calculus, you have seen some already. An example is the differentiation operator, d over dx. If we were doing algebra, we could have divided the numerator and the denominator of this fraction by d, and we would have just ended up with 1 over x. Of course, this isn't something that you can do in calculus, because d over dx isn't just an algebraic expression. It is a symbol that tells us to take the derivative of the function on its right with respect to x, according to a rule known to us. The differentiation operator, in and of itself, does not have a value until we give it a function to act upon. Depending on the function that we give it, it will produce different results. If f of x equals x squared, then acting on it with the differentiation operator returns to x. If we give the operator a different function, say an exponential, we will get a different result. Operators are often denoted by letters with a hat on top. An operator A is called linear if it satisfies the following condition. That is, there should be a distributive property for it. The operator acting on a sum of two functions should be equal to the sum of the operator acting on the first function and the operator acting on the second. Furthermore, it should be possible to pull any real or complex constants that the functions are multiplied by out from inside the operator. Let's consider a few examples. Is the square root operator linear? To check this, we write out the linearity condition and ask ourselves whether it is true. Of course, in this case it isn't, so we conclude that the square root operator is not linear. In principle, an operator can be just a function. For example, if a is x squared, then it tells us to multiply the function f of x by x squared. Since multiplication is distributive, the linearity condition holds, and the operator x squared is linear. The differential operator of arbitrary order n is also linear, since the linearity condition is satisfied for it too. All operators used in standard quantum mechanics are linear. There are extensions of quantum theory that employ nonlinear operators, but they are used for rather advanced applications that we will not be covering in this class. In quantum mechanics, a correspondence is established between physical quantities that can be measured, often referred to as observables, and linear operators. On this slide we have listed a few examples. Perhaps the most important operator in quantum mechanics is the Hamiltonian, the operator that corresponds to the total energy of a given physical system, and that can be written as a sum of the kinetic and potential energy operators for that system. Other important examples are position and momentum operators. It is easy to show that these operators are linear, in the same way as we have done earlier for other operators. For an operator capital S corresponding to physical quantity or observable small s, the values of s that we might find by measuring it are given by the following eigenvalue equation. Here, Sn is the nth allowed value of s, the eigenvalue of operator capital S. Psi n of x is the wave function corresponding to this eigenvalue. It can be shown that an arbitrary wave function psi of x, corresponding to some state of a particle, might be written as a linear combination of eigenfunctions psi n of x, that is, as a sum over those eigenfunctions, each multiplied by its own coefficient Cn, that can in general be complex. Quantum mechanics is a probabilistic theory. When we measure the observable S, we usually don't know exactly what result we will get. However, the probability of getting each possible value Sn is given by the square of the absolute value of the coefficient Cn in front of the eigenfunction psi(n) that corresponds to eigenvalue Sn in the expansion of the wave function psi. The final topic that we need to talk about in this video is that of commuting operators. Let's say we have two observables, small s and small q, that correspond to linear operators capital S and capital Q. The eigenvalues of the operator capital S are Sn, and its eigenfunctions are psi(n). The eigenvalues of the operator capital Q are Qn, and its eigenfunctions are phi(n). The operators S and Q are said to commute if for any allowed function f of x, the following condition holds. When we see two operators acting on a function, it means that the operator that is closer to the function acts on it first, and the other operator then acts on the result. It is easy to see that not all operators commute. Consider the example of the position and momentum operators in 1D. The momentum operator is a differentiation operator times a constant. Thus, acting with it on the function f of x and then multiplying the result by x is obviously not equivalent to first multiplying f of x by x and then differentiating the product. On the other hand, if we consider, for example, the operators x and y that correspond to the coordinates of a particle in 2D, the order in which these operators multiply a function f of x and y is irrelevant. Thus, these operators commute. It can be shown that if two operators S and Q commute, then they share a common set of eigenfunctions. This is important in quantum mechanics because measuring an observable changes the wave function of the system. After the measurement, the wave function becomes some eigenfunction of the linear operator corresponding to the observable measured. Since each eigenfunction corresponds to a well-defined eigenvalue of an observable, then if two observables share an eigenfunction, it means that their values are simultaneously well-defined. Otherwise, this is not the case, and the values of observables that correspond to non-commuting operators cannot be known simultaneously to arbitrary precision, in accordance with Heisenberg's uncertainty principle.